So welcome everybody to our presentation. My name is Malena Cazorla Martínez, and I finished my bachelor's thesis and my bachelor's degree 2 years ago in the University of Barcelona. And I am currently doing my master's degree in the University of Geneva in the orientation of geochemistry, alpine tectonics, and ore deposits.
And I'm Gemmrich Hernández. I also finished my bachelor's degree in the University of Barcelona 2 years ago. And this last year, I finished my master's degree in mineral resources, also in the University of Barcelona.
So we are both part of the Barcelona SGA student chapter. And before starting our presentation, we would like to thank the SSG and all the organizers of this symposium for giving us the opportunity of sharing our studies and our projects. And we would also like to thank Dr. Joan Carles Megarejo Drape and Dr. Lizard Turroyabat, which were our supervisors of our bachelor's thesis and also the supervisors of my colleague Laura master's thesis. So yeah, during this presentation today, we will talk to you about the resources of critical elements in Bolivian Tin Belt deposits. This is going to be the outline of the presentation. First of all, we will introduce to you the main critical elements studied and discussed in this presentation, then the area of study, and finally the main objectives of the project. And then we will start reviewing some of the studies from this project. The first one is going to be focused on sulfides and sulfosalts based in the Animas, Chocalaya Suyos district.
And the second one will be focused on oxides on a larger regional scale. We will then together make some final remarks and conclude our presentation.
So to start with the introduction, the main critical materials studied and discussed in this presentation are indium, germanium, and gallium, and also niobium and tantalum. And as we can see in this graph to the left, prepared by the European Commission this year, where we have some materials plotted in this graph that is economic importance versus supply risk. And we have they have determined two different thresholds. And all these materials that plot above these two thresholds are considered critical for the development of the European society. So as we can see, here is gallium, here is tantalum, here indium, here germanium, and here niobium. So they are plot above these two thresholds, so they are considered critical. And some of the main uses of these elements are, for example, for batteries, for touch screens also, and also for the manufacturing of solar panels and also electric cars.
So our area of study is the Bolivian Tin Belt, which is located in the Bolivian Andes in southwest Bolivia. This area presents a marked morphotectonic partition that reflects differences in geological history, paleostructural domains, and in the current crustal structure. These domains are from west to east, the Western Cordillera, the Altiplano, and the Eastern Cordillera. The Bolivian Tin Belt is here in red, a metallogenitic province located in the Eastern Cordillera, and its tin, tungsten, silver, and base metal deposits are world-renowned and the focus of our studies. This area is mostly composed of late Miocene to recent and intermediate filthic igneous rocks that intrude in and extruded over Jurassic and Cretaceous sedimentary and volcanic rocks. The studied deposits belong to the epithermal and xenothermal environments. So what does xenothermal environment mean? This environment is characterized by polymetallic high-temperature vein deposits with high temperature, meaning between 300 and 500 degrees Celsius. These vein-type deposits are emplaced in the sub-epithermal environment. So in 2019, the Bolivian Tin Belt accounted for about 6% of the global tin production, in addition to silver and tungsten. And it is estimated to contain more than 8% of the world's tin resources.
So regarding the main objectives of our project, so as I said before, this is a big project that englobes different minor studies. So this project started with the main objective of seeking a better understanding of the parameters that control these high-tech element contents and enrichment in the Bolivian tin deposits. And we wanted also to know get to know some of the geochemical tools for their exploration. So some of the specific objectives of the project include, for example, determining trace element content, such as the ones that I showed you in the first slide, in sulfides, sulfur salts, and oxides. And once we have determined this content, we can then identify which mineral phases concentrate preferentially these critical elements. Then we also want to understand the spatial distribution of trace elements along single deposits, and if possible, in a regional scale. And then we want to understand the timing of trace element enrichment along the paragenetic sequence. So if this enrichment occurs in the early paragenetic sequence or in the late stages. We also want to determine the physical chemical conditions that are favorable for the transport and deposition of high-tech metals. So if there's like a specific mechanism for the enrichment of these mineral phases in these critical elements. And finally, we want to know if these analyzed trace element contents are found in economically important values in Bolivian Tin Belt deposits. So now I'm going to start to review this first study from this project. So this is based in the Animas Chocalaya Suyos district, and it's mainly focused in sulfides and sulfur salts that are indium rich. So regarding the geological setting, it is geological and geographical setting. It is located pretty close to the triple joint between the Eastern Cordillera, the Western Cordillera, and the Altiplano of the Andes. And it's also located within the Bolivian Tin Belt that my colleague just explained to you. And now if we take a closer look to the study area, here in the right image, we have a more detailed geologic map of the district. And as we can see, it's mainly composed by rocks that are part of a volcanic caldera complex, which are hosted by Oligocene, Miocene sandstones and tuffs, and also Ordovician sandstones and slates, which are these pink and brown. So the volcanic rocks would be these colors here. And here in this image, we can see all the different samples that have been collected throughout the different field campaigns that have been done to this mine in our project. So as we can see, these are distributed all along the surface of the district, but also in depth, so that we can have a better understanding of the distribution of the elements, the critical elements in the surface, but also in the depth. So just to make clear, this district is divided in 3 different mines. So the first one is the Chocalaya Mine. Then we have the Animas Mine, and then we have the Suyos Mine towards the north. And regarding the petrological study, the 3 different mines, they have more or less a very similar mineralogy, but they have some minor differences. So, for example, in the Suyos Mine, this sphalerite contains in some places some chalcopyrite blebs, which has been determined as chalcopyrite disease. And we can also observe that the sphalerite is banded in some places, and it's cross-cut by stannite. And regarding the Animas Mine, the stannite content is much higher, and we can also observe a huge variety of sulfur salts, such as the ones we can observe in this image, for example, gemsonite or andorite or mearterite. And regarding the Chocalaya Mine, so this one is simpler than the mineralogy of the Animas and the Suyos Mine, as far as we have seen. So it's mainly composed by a pyrite marcasite assemblage, which contains some small pyrrhotite grains that we will refer to as pyrrhotite remnants. And we can also observe some veins that cross-cut this assemblage of pyrite and marcasite composed by sphalerite and galena. Regarding the ore mineral geochemistry, So we did electron-proof microanalysis in the grains of the samples that we collected. So some of these microanalyses were performed in sphalerite grains, and we obtained values of indium up to 9.66 weight% in the Siete Suyos mine. And we could also observe a very high value of indium in stannite, but in the Animas mine, which is up to 4.11 weight%. And we could also observe some other indium-bearing mineral phases in the Animas Chocalaya Suyos district, such as rhamdorite or wurtzite. But these contents were not as high as the ones found in sphalerite and stannite. Now, regarding the incorporation of indium in sphalerite and stannite structure. So as we can see in this graph in the left, it's for sphalerite. So here we plotted all the electron-proof microanalysis that we performed in sphalerite grains in this copper versus indium diagram. So as we can see, they all plot or within this line that it's copper indium 1 or above this line. So basically what we concluded with this graph is that we need copper in the environment in order to incorporate indium in the sphalerite structure. So this could also be observed in this SEM-EDS qualitative X-ray images. So these bands that are indium rich and also copper rich, which are the lighter bands, are also depleted, so impoverished in zinc. So we could say that we have a couple substitution between zinc substituted by copper plus indium. And then regarding stannite, we could observe a correlation between copper and indium and tin and indium. So we could conclude that indium enters in the stannite structure, replacing the positions of copper and tin. And regarding the spatial distribution of indium in this deposit, we could see that in the case of sphalerite, towards the inner parts of the deposit, we have a higher content. And when we go towards the outer parts of the deposit, this indium content tends to decrease. And the same was observed for stannite grains. And in depth, we could also observe some trends. So in some of the veins studied, for example, the Animas vein, we could observe that towards the deeper levels, we have an increase in the indium content, in the average indium content. The same for the Arturo vein and also for the Chorro vein. And finally, regarding the paragenetic sequence and the evolution of the fluids, we could distinguish, thanks to the petrological study and the electron-proof microanalysis, that there were three different stages. A first one that it's low sulfidation, and a second and a third one that it's intermediate sulfidation. So we can see that there's a shift from low sulfidation to intermediate sulfidation. So some characteristics of the low sulfidation assemblage, for example, are these pyrrhotite remnants that I showed to you in the Chocalaya mine. And we could also observe iron-rich sphalerite, whereas in the intermediate sulfidation stages, we could observe iron-poor sphalerite, which is typical for the intermediate sulfidation assemblages. And how is this related with the indium enrichment? So we could see that the sphalerite in the intermediate sulfidation stage, it's much higher, so much more enriched in indium than the sphalerite from the low sulfidation stage. So this was all for the Animas Chocalaya Suyos district, and now my colleague is going to continue with the second study.
So our latest study was focused on cassiterite, as it is one of the major components of the Bolivian Tin Belt. Cassiterite, due to its structure, can incorporate a wealth of elements in minor and trace concentration in substitution of tin. So some of these elements, as stated before, are considered high-tech metals critical to global economy. And this would be like indium, germanium, gallium, niobium, and tantalum. And since cassiterite can form in a broad range of pressure, temperature, and composition conditions, and has a high physical and chemical resistance, it can be useful as a petrogenetic indicator. And also, due to its ability to incorporate elements such as uranium and lead and its high closure temperature, it can be used for dating. So in this study, we determined the geochemical composition and uranium lead ages via laser ablation ICP-MS of cassiterite samples belonging to 9 deposits from the Bolivian Tin Belt. The studied deposits represent different ages, depths of mineralizations, and proximity to intrusive ore bodies. So the shallower deposits would be represented by Poopo, Polquechaca, and Animas and would belong to the epithermal environment, whilst the deposits of Queluani, Biloco, Oruro, which would be the San Jose and Itos mines, and Yayagua, Guanuni, and Boriwari would belong to the xenothermal environment. We determined that the mineralization occurred in 2 distinctive stages. In the northernmost part of the Bolivian Tin Belt, represented by the Queluani deposit, mineralization occurred during a rifting episode about 240 to 220 million years ago. And in the southern part, represented by the deposits of Biloco, Guanuni, and Yayagua, mineralization occurred during a major episode of basaltic magmatism about 24 million years ago. So even though the mineralization occurred in 2 different stages, spaced out in time, the composition of studied cassiterite samples is relatively homogeneous. As cassiterite is tin oxide, the composition of tin is mostly around 97 to 99% in weight. Cassiterita from the Bolivian Tin Belt is also enriched in iron in some deposits, such as in the Oruro area. It can reach up to 2.32% in weight. Some deposits of the Bolivian Tin Belt are also enriched in titanium, such as the deposit of Queluani, and in other deposits, such as in Biloco and Guanuni, there can also be found an enrichment in niobium. In regards to trace element concentration, we can also see 2 distinctive trends. One of depletion towards the south in elements such as titanium, vanadium, chrome, niobium, and tantalum, and on the contrary, one of enrichment towards the south in elements such as indium, gallium, germanium, and arsenic. Some nuances in trace element contents of deposits and mineralization emplaced at different levels allow for the identification of some compositional trends. So deposits formed adjacent to causative intrusive complexes, such as the deposit of Queluani, Biloco, and Yayagua, are typically enriched and niobium and tantalum related to shallower deposits and the epithermal and xenothermal environment. In addition, there are 2 ratios which can give us information about the proximity to hydrothermal centers, which would be the titanium-zirconium ratio and the titanium-scandium ratio, because we can see that the deposits more close to these higher temperature areas are enriched in these ratios, and these ratios decrease towards the outermost deposits. We can also see there's an enrichment of iron towards the shallower deposits. And finally, as for the concentration of critical elements, we can see that the concentrations of niobium and tantalum can reach about 1,000 to 2,000 ppm in niobium from the Queluani and Biloco deposits, and the concentrations of tantalum can reach about 114 ppm of tantalum. But when we compare these contents to cassiterite from magmatic environments and other sources, they are not as high. So therefore, cassiterite from the Bolivian Tin Belt would not be likely a good resource of these metals. This would also be the case for germanium, since its concentrations in the studied samples are systematically very low and always below 10 ppm. This would, on the contrary, not be the case for gallium or indium. So the gallium concentrations can reach up to 7,400 ppm in the Animas Chocalaya district, and about 1,300 ppm in Oruro. These concentrations are consistent and often higher than concentrations reported in some bibliographic studies. And this would also be the case for indium, which can reach concentrations above 1,000 ppm in Oruro, Wari-Wari, and Animas Chocalaya, with the highest concentrations that were found in Oruro from 1,300 ppm. However, the concentration of these elements in cassiterite is not as big as in sulfides, which we will now discuss.
So now the final remarks of the two studies that we have just reviewed. Laura, if you want to start.
Yes. So when we talk about critical element content, we have seen that sphalerite and stannite are usually present higher concentrations of these critical elements when compared to cassiterite. But in the case for cassiterite, the concentrations of indium are much higher than the concentrations of gallium, and these ones are higher than niobium, tantalum, and germanium, which would be relatively small.
And regarding the indium enrichment in some of these spaces, so for example, in sphalerite, as we could see before, this enrichment is correlated with the copper content. So we could conclude that when we have a sphalerite that is rich in copper, it could be also possible that it's also enriched in indium.
For cassiterite, the concentration of indium generally depends only on the content of indium from the mineralizing fluid. And when we talk about spatial distribution of critical elements on the regional scale, and when we talk about cassiterite, we can see that the northernmost deposits are usually enriched in niobium and tantalum, and the southernmost deposits would be enriched in indium and gallium.
And regarding district scale, so smaller scale, we can see that there's an enrichment of these elements towards the inner parts of the deposit, in the case of Animas Chocalaya, for example, and towards the outer parts, we have a decrease in the content of some of these critical elements. And we could also observe this in depth. So towards deeper levels, we can observe that we have a higher indium content. And regarding temporal distribution of critical elements, so at least, in most of the deposits in the Bolivian Tin Belt, we can observe a shift from low sulfidation to intermediate sulfidation throughout the paragenetic sequence of the deposits. In the case of Animas Chocalaya district, we have the indium enrichment in the intermediate sulfidation assemblages. So this is not the same in other deposits. For example, in the Wari-Wari deposit, which was the one that my colleague Laura studied for her bachelor's thesis, where she could observe that the enrichment of indium takes place in the low sulfidation assemblage, so in the iron-rich sphalerite. And finally, as a last question, are these trace element contents found in the Bolivian Tin Belt deposits economically relevant? So for answering this question, we prepared this graph where we have the maximum contents of indium found in the studies from our project. So in orange would be the sphalerite, and on green the stannite, and on blue the cassiterite. So in the case of sphalerite and stannite, we can see that the higher contents of this critical metal are found in the Wari-Wari and Animas Chocalaya mines and districts.
And for cassiterite, generally the concentration is higher also in the Wari-Wari and Animas Chocalaya mines, but in the area of Oruro, so in the San Jose and Itos mines, there's also a high concentration of indium in cassiterite, which it would be interesting to look at the sulfides in this area because they may also be enriched in indium.
Yeah, so something we want to point out is that to get to know if these critical elements amounts found in these deposits are economically profitable, we need to combine these geochemical studies that we have performed with further metallurgic and mining focused studies that we hope to be able to perform in our project in the future. So this was all for today. Thank you very much for your attention. We hope you enjoyed the presentation. And yeah, this was a very nice moment, very funny moment in one of our field campaigns that we did in Bolivia for sampling some of the deposits that we were going to study. So yeah, we have here the llama and we are scared, but but it was a funny moment anyway. So thank you very much for your attention, and yeah, once again, we hope you enjoyed it.
And enjoy the rest of the presentations.
Yeah, of course. Bye bye, and thank you again. Here you have the references, so the main articles that were cited in this presentation, and yeah, finally the other references that we used and cited throughout the presentation. So yeah, bye bye, and thank you so much.
Bye.